In today's session, I'll be demonstrating how I can measure internal resistance of a cell coming up. So the procedures for measuring the internal resistance of a cell like this one are very simple. We're having a dry cell right here, a voltmeter, and a rheostat. This is a resistor whose resistance is variable, but in this case, we need a resistor whose resistance is fixed. And for this rheostat, I've fixed its resistance to its maximum, which is 20 ohms. First of all, we shall be finding the potential difference across the ends of that cell. So we're going to connect our voltmeter across the terminals of a dry cell. And in our previous video, we said that the voltage across a cell, when no current is being drawn out, is what we call the electromotive force or the E.m.f. of that cell. So here's how we are going to do it. This is our dry cell right here. That's the negative terminal right there, and that's the positive terminal right there. And this is our voltmeter. As you can see, its initial reading is 0. So we connect the negative to the negative terminal right there, and then the positive terminal we connect it to the 3 volt terminal. We're going to connect this to the 3V terminal, and when we connect it to the 3V terminal, this positive terminal of the cell, if we connect it to the 3V terminal, it means we'll be using the upper scale as our scale, not the lower one but the upper one, because it is the upper one that is having 3 volts at its end as its full scale deflection. So we'll go ahead and connect this right there, and our thing has deflected, the voltmeter has deflected. If you can observe very clearly, our cell, the voltage is around 1.1 to 1.3. It's between 1.3 and 1.4 volts. So after getting the voltage across the cell, of course, the E.m.f. of this cell is supposed to be 1.5, but this battery is a bit used, so that's why it's not deflecting to 1.5. It's actually 1.3, 1.4 volts. So after doing that step, now we know the E.m.f. of this cell. Now we'll go ahead and connect a resistor of known resistance R. So after we have done that, now we are going to connect a resistor of known resistance R into our circuit so that we are able to get another value of V. Now we expect that when we connect a resistor onto that cell, it means that now we're going to be drawing current out of the cell. And of course, if we are drawing current out of the cell, we expect the voltage across the terminals of this cell to drop. So we're supposed to connect a resistor of known resistance R. So in essence, I'm supposed to be connecting a resistor to this circuit whose resistance I know. I'll use my rheostat. I know its maximum resistance is 20 ohms, so I've set it in such a way that its maximum resistance is 20 ohms. And so when I connect my rheostat, my voltage is still about 1.4. It's in between 1.3 1.4. When I connect my rheostat, what happens to the voltage, the value of V? When I connect, it drops drastically. Voltage has dropped drastically to 0.1 volts when I connected my rheostat. Now we assume that this has been set to 20 ohms. It's at its maximum, so the voltage has dropped to 0.1. And now after getting that, then we get into the mathematics to get the internal resistance of this cell. Now if we may go back to a clip from our previous video, this is what we concluded about the equation of E.m.f. Previously, we've been calculating voltage, current, and resistance of the cell while ignoring the internal resistance. We've been taking the internal resistance to be negligible. But if the internal resistance is not to be ignored, it means that we're going to treat this resistor as if it is a cell that is in series with the rest of the resistors in the circuit. So if this, let's say this is capital R, that's the resistor. We all know that to get the total PD in the whole circuit, which is, we know that PdV is going to be equal to I times R. Total potential difference is going to be I times R. But then we know that the potential difference across the terminals of a cell on an open circuit, which is the source of the PD in the whole circuit, V, is what we are calling the E.m.f. We said E.m.f. is the potential difference across the cells when no current is going out of it. And we all know that it is the cell that is the source of the potential difference in the whole circuit. So this potential difference across the terminals of the cell, the source, when there is no PD, is what we're calling E, is going to be equal to the current flowing through the circuit, which is capital I, times resistance. Now remember, now when it comes to resistance, before, when we were not considering the internal resistance, we were just looking at R, the resistance in the circuit. So meaning that if you're having whatever like resistors in series or parallel, all you had to do was to just simply get the effective resistance and you would calculate it. But now when we are talking about the internal resistance, it means that now we have a new resistance in question. If we were to call internal resistance R, this is our effective resistance, it would mean that it's going to be capital I, which is the current, times R, which is the effective resistance outside the circuit, plus that internal resistance R. So we treat this resistance as though it is in series with the external effective resistance of the circuit. And so this becomes our equation for e.m.f. So our equation for e.m.f. is that electromotive force, which is the total PD in the whole circuit, is going to be equal to the current flowing through, that is the current supplied by the cell, times the resistance, the total resistance in the circuit. And the total resistance in the circuit comprises of the resistance of the other resistors in the circuit, the effective resistance, plus the resistor that is inside the cell, or called it the internal resistance. We add R plus R. We add it like this because the internal resistance and the effective resistance outside the circuit are in series. If we have to open these brackets, it simply comes to be electromotive force is going to be equal to the potential difference across the external circuit, and this is what we are calling the terminal PD, plus the potential difference across the internal resistance. And so we are going to use that exact equation to conclude here, to find the internal resistance R. So how we go about it, we, like earlier said, E is equal to voltage across R plus voltage across the internal resistance. Now voltage across R is E is equal to IR. Now the voltage across the R, the rheostat that we used in our resistance, capital R, is going to be the current that was flowing times capital R plus the current times still flowing in that circuit times the internal resistance R, which we are looking for. Of course, when we get this to go that side of the equation, it becomes E minus IR is going to be equal to capital I times R. When we make R the subject of the formula, we have E minus IR is equal to, or divide that by I. Now, looking at this equation here, we have capital E, which is the EMF of the cell, which we got in the very beginning when we connected our voltmeter across the terminals of the cell when no current was being drawn out of it, and I think I remember us getting around 1.3, 1.4 volts, minus the current going through the circuit. Now, in our experiment, we didn't engage any ammeter, so we do not know any I. We do not know the current that was flowing through the circuit. But we do know the resistance that was connected in the circuit, and that was the 20 ohm resistor. And for our case, it was 20 ohms. Now we do not know this value of I. So it means that we are going to eliminate this I. From Ohm's law, we know that V is equal to IR. Since we do not know I, we are going to eliminate it. So we are going to substitute for I using this. So when we make I the subject of the formula here, we have V over R. We know the voltage when we connected the resistor. When we connected the 20 ohm resistor, we know the voltage that we were attained. It was around 0.1, and then we also know the resistance. Again, from our equation right there, it's going to become E is going to be, where there is I, we put V over R. We're getting this from Ohm's law times R. Divide that by I, which we are still going to substitute here as V over R. Of course, from here, this value of R, this R is going to cancel with that R, you remain with V, so it becomes E minus V on top here, divide that by V over R, and now this is the same. When we find the reciprocal of this, it becomes R, becomes the internal resistance is going to be R, which is the 20 ohms, into capital E, which is the EMF, minus V over V. So this is the equation, this is the formula we use to find our internal resistance. This brings us to the end of this video. Thanks for watching. Feel free to check out other excellent videos on the channel and don't forget to subscribe. For Kisembo Academy, this is Arnold Rangakuramia helping you manifest excellence.